All right, welcome everybody. I think this is lecture 15, and it's more on hypothesis tests. So let's just start by doing a hypothesis test. Suppose your research indicates that the average number of spines on can I get an animal with spines? I've never met a dog that has spines. That's super interesting. Okay, porcupine might work. I want to do sea urchin. Because if you're interested in biology, there's a lot of great opportunities to do research in tidal areas. Yeah. I'm trying to get the focus set a little better here. Oops, hold on. Okay. The average number of spines on sea urchins is 250. But you are collecting adult sea urchins. Oops. In a Lincoln City tide pool. And you are starting to get suspicious with what you notice. All right. There seem to be fewer than 250 spines on a lot of the urchins you collect. Most research starts with something that we notice. Now, you can't just say, well, since most of these have fewer than 250 spines, that gives me evidence, right? If we're going to try to challenge some research, whether that's the literature or your biology graduate professor or whatever, we need to have a systematic way to do it. So noticing it is a great first step. You can just say, something seems weird. But if we're going to formally challenge research, we need a formal process. So let's challenge this with a hypothesis test. So let's conduct a hypothesis test with the 9 steps. Feel free to grab your notes from last Thursday. What's my first step for hypothesis test? A research question, often framed as a yes or no. What could we write as a research question based on what you notice? Yeah, so we could ask, have the average number of spines decrease? That includes a time element. Or we could ask, are the average number of spines in Lincoln City sea urchins equal to 250? Right? Maybe it's not a time thing. Maybe it's a location thing. Who knows? Like a lot of possible research questions. But let's use yours. Have the average number of spines on sea urchins decreased since, let's say, since the research was published. that has the advantage of being a yes or no question. And of course, you can have research questions that aren't yes or no. You just wouldn't use a hypothesis test to explore them. In fact, we do have a great test, a great tool for exploring a research question that might say, what's the average mass of sea urchins? You wouldn't use a hypothesis test for that. What tool would you use if we just wanted to know what's the average weight or the average mass? What statistical tool could give us information about that average weight of sea urchins? It's probably distributed normally, right? That would be an important piece of the tool that we used. Would we use some sort of binomial testing thing? No, because it's not a yes/no question. Yeah. We're trying to estimate the average. What would we use? What tool would we use if we were just trying to estimate the average?
A simple average?
That would be part, we would take a simple average. I'm looking for a different answer though. Take a minute, talk to your neighbor. What do you think, Lily? Absolutely, if we were just trying to do a research question that was open-ended, like what's the average weight of a sea urchin, we could collect a sample, find the sample average, and then create a confidence interval. That's a fantastic way to answer that type of research question. This type of research question is comparing different groups. Right? We talked about in our rules of statistics rules of 3. Let me see if I can find it. Here we go. Here's our statistics rules of 3 types of statistics. Inferential, understanding populations. What's the average weight of sea urchins? Confidence interval. Hypothesis testing, understanding differences. Is there a difference in the number of spines now compared to earlier? That's when we would use a hypothesis test. And then in a week or so, we'll talk about regression analysis, understanding relationships in our systems. So anyway, that was an aside. This being a yes/no research question focused on a number is a great way to pose a research question for a hypothesis test. What's our next step? Exactly. The null hypothesis and the alternative hypothesis. The null hypothesis is the boring answer. What's our boring answer to this question? Has the average number of spines changed? No, that's boring. Nothing to see here, right? Might as well study something else instead of studying something that hasn't changed. No, it hasn't changed. And we might write this as saying the average number of spines is still 250. Right? If we wanted to make it a little bit more mathematical, or at least so close that we couldn't say there's any practical difference or statistically significant difference. And what would be the interesting answer? Yes, it has decreased, because now we get to ask the cool question, which is why? Yeah. Alternative. Oh, and let's look really carefully at Francis's question. The question was, has it decreased? I'm not just asking, is this different, but actually, has it decreased? So the answer would be yes, it has decreased. So if I wanted to put that mathematically, I would say the average number of spines is now less than 250. This is called a one-sided or a one-tail hypothesis test, where my alternative is not simply that it isn't 250, but that it's actually less than 250, or maybe in another world, greater than 250. So we can do one-sided or one-tailed hypothesis test. We can also do two-tailed. The default, if nobody tells you otherwise, is a two-tail. But this one, the way we phrased, one tail is just fine. Yeah. Okay. What's our next step? We need to pick a significance level before we go out starting to collect our data so that we don't use our data and have it unconsciously influence us. Significance level. This is our probability cutoff, because remember, statisticians make their decisions based on probabilities. Anybody have a suggestion for what we want that to be? 5%. If nobody tells you otherwise, make it 5%. What comes next? Collecting data. Get your boots on. Go out to Lincoln City. Hope that the tide's right. You know, check the tidal charts. Hope it's not raining too hard. And you're going to spend a couple hours out there counting spines. The hardest part of any statistics is collecting good data. So let's collect the data. And let's say that we have 32 urchins. I'm not going to list out sea urchins. I'm not going to list out all of their spine counts, but let's imagine, right, we have that with counts of spines for each. Right? We can sit down. I mean, we sat down, and except for my kind of wandering tangent over there, we did steps 1 through 3 in about 2 minutes. That's the easy part. Step 4 would take us minimum of a day, right? It's the hard part. And often statistics class gloss over it. And unfortunately, I have to as well. Although I would love to spend a day on the beach with all of you counting sea urchin spines. I think that would be super fun. Maybe you get to do it in an ecology class. If you do, let me know. I want to come and I can help with the statistics. What's next? Now we compute some sample statistics. In this case, since our hypothesis test is about a mean, we want to know the sample mean. So out of the 32 urchins, we found the sample mean X bar was 238 spines per sea urchin. And because we're going to use a central limit theorem, we want the standard deviation. Well, we're going to start by collecting the standard deviation of the sample. Which was 18 spines. Right, so on average, they had 238. A couple of them had up to 270, maybe even 280. A couple of them were all the way down at like 200, right? We had a wide range. We need one more sample statistic if we're going to do our actual hypothesis test. It's not from data we collect, it's a number that we calculate based on the data that we collect. Because we're asking about means, not individual observations. So we need the standard deviation, not of the sample, but of the sample means. Right, the STDev of X bar. What's the formula for that, for calculating that?
Standard deviation.
Right, it's the standard deviation of your sample divided by the square root of your sample size, which I should have written n, but I wrote 32. N equals 32. So this number here is going to be 18 divided by the square root of 32, which is approximately 3.2 2. And technically, we still have units on there, spines. That tells us that if we were to collect another sample, we think there would be 238 average in that sample. But, you know, maybe the sample average would be as big as 246, maybe as small as 230, somewhere in that area. Much bigger and much smaller would start to be surprising based on the data we collected. Now, you can do a hypothesis test about a proportion. Then you get a p-hat, a sample proportion, and you get a standard deviation of your sample and a standard deviation of your sample proportion as well. You can do a hypothesis test about a median, about a standard deviation, about all sorts of different things. We're focusing on the mean because A, it's the most common, and B, the idea transfers to whatever statistic you're looking at. What comes next? We do the actual hypothesis test, all right, where we calculate probabilities. And for that, we use technology. If I actually had the raw data, I would use R for that. All right, I would just put that raw data in. Since I don't have that technology or the raw data, I will use different technology, which you can use on your homeworks, for example. Where is it? There it is. We're going to use our normal distribution. So under the null hypothesis, make sure you'll be able to read this. The expected sample mean, right, the expected value of X bar, E of X bar, that should be 250, right? In the boring world, we should be looking around and seeing pigs, not Technicolor flowers. And the standard deviation of X bar, we don't know, but it should be close to 3.2 because that's our best guess based on our data. And so that's how we build our normal distribution. I'll draw it here. You don't have to draw it when you do your own test. It can help thinking about it. That's 250, and each step should be about 3.2. So that's what we'll do here. We'll put a 250 and a 3.2. It always gives us the same shape bell curve. What changes is the scale. And then our actual observation was down here at, what was it, 238? So since this is a one-sided hypothesis test, we're actually just going to calculate the value to the left of 238. 0.01%. I mean, we can't even see it here, but it's so much smaller than what we would expect. And that was the hypothesis test. The probability of a sample mean less than 238 is about 0.001 or 0.1%. Oh, 0.01%. There's even an extra zero in there. So 4 zeros. Who cares exactly how big it is? It's tiny. And I encourage you to think that way as well. If you get a number this small, we don't need to know that exact probability. We just need to know that it's smaller than our cutoff. The fancy word for this probability, do you remember? Did someone say something? This is called the p-value. But if you always want to think about it as the probability of observing data more extreme than what you have, that's good because that's what it actually is. So the p-value is about 0.0001. Is that smaller than our cutoff? Yeah, that's way smaller than 0.05, which is our significance level. What's step 7? Oh, okay, cool. That was step 7 right there. We compared it to our significance level, and that tells us what? Which hypothesis are we going to go with? We're going to go with the alternative. Because in a world where this is so unlikely, we say, well, we're probably not in Kansas anymore. We're in a world where the average number of spines is less than 250 now. So we conclude that the average number of spines has decreased since the previous research was published, i.e., we reject the null hypothesis. But if you just say to someone, I reject the null hypothesis, unless they're a statistician, they're not going to know what you mean. It's better to say, I conclude that the average number of spines has decreased since the previous research was published. All right, it's not like Dorothy looked around and said, I reject the null hypothesis. She told Toto something that Toto could actually understand. You think Toto understands the word Kansas? I think so. No, probably not. My cats know lots of words, but I don't think they know the word Oregon because it doesn't matter to them. Cool. What's step 8? Yeah. So we've concluded that this is statistically significant. But now we ask ourselves, is this practically significant? And what is the ethical significance of this result? It's okay if you can't answer that. First of all, I made up the data. Second of all, I'm not a marine biologist. I don't know if 238 is meaningful or not. But that's why statisticians usually work in research teams. We take back the statistical conclusion and then we have a conversation with the research team and we say, what do you think? Do you think 238 is really that much of a difference? And they might say, no, they're still, they're still populating the area, or they say, yes, we think that's really important. And then the same thing with the ethical significance. I don't know because I'm not a marine biologist. This isn't necessarily a question we can answer, but these are questions that we should ask. And then step 9. Yeah, ask a new research question. Ask a new testable research question, and or offer a testable scientific explanation. All right, so you might say, well, ocean temperatures seem to have been going up. Maybe that's affecting them. And so then you do some comparisons and you find some parts of the ocean where temperatures haven't changed. And you compare into parts of the ocean where temperatures have changed. And you say, well, is the number of spines changing? All right, but you extend your research with a new research question. And there you have it. There's a hypothesis test from start to finish. And again, I mean, it took us half an hour total, but that was really quick considering people get published with this, this sort of work. The hard part is collecting the data. All right, now it's time to start talking about some of the details of a hypothesis test. And my first question is, what is a chance that we come to the wrong conclusion based on our data. So let's use this example. Suppose there really is no decline in the number of spines. Is there a chance that we would incorrectly reject the null hypothesis? If there is, how big is that chance? So take a few minutes, talk with your neighbor about those questions. As soon as we pick our significance level, we have set the bar for making this mistake. Right? There is a chance, and the size of that chance is exactly our significance level. Because the whole point of a significance level is it's our cutoff for rejecting. Any probability less than the significance level will lead to rejecting the null hypothesis. But by definition, a probability means we could be wrong. If this picture is true, where the mean is in fact 250, the expected value, and each step here is 3.2, then if this is our rejection region, if these probabilities represent when we're going to reject, anytime we're in here, it's telling us there's a 5% chance that we shouldn't be in here. All right, it's what Lloyd says when, does anyone remember Mary? I don't remember. When she says more like 1 in a million, well, there's still a 1 in a million chance they could get together. So as soon as we pick our significance level, we have the bar for rejecting the null hypothesis when we really shouldn't have. And there's a name we give to this error. The error of rejecting the null hypothesis when it is actually true is called type 1 error. We often think of this as a false positive. Right? If you're doing ecological research and you're like, oh my goodness, the number of spines has decreased, but it actually hadn't, that's a false positive. In medicine, it would be saying something like, I think you have diabetes because your scores on your A1C are very high. I guess that's how you define diabetes, though, right? So that wouldn't happen. But let's do like prostate cancer, right? If you have a lump on your testicle, you might be diagnosed with prostate cancer, but once in a while that's actually benign. And so you didn't have it, that's a false positive. How do you correct it in that case? You do more testing. Yeah. Are there ways of minimizing or making this probability making the chance of a type 1 error smaller. So can we reduce the chance of type 1 error? And if so, how? Yeah, we could change our significance level. We could make it harder to reject. Make it harder to reject the null by choosing a smaller significance level. If we chose a 1% significance level, then there's only a 1% chance of type 1 error before we even start collecting our data. That's a good way to do it. Any other ideas? Collect more data. Why stop with 32? If we're worried about getting the wrong result, we could go out and we could collect 70, right? Because then our estimates are going to be more accurate. Okay, so we could also collect more data, which makes our statistical analysis in whatever type of statistical analysis, whether it's a confidence interval or a hypothesis test or anything else, statistical analysis more accurate. Now, there's a drawback to both of these. And I'm going to talk through each of the drawbacks. The first one, the drawback to reducing the significance level. Can anybody think what that might be? If I make the significance level 1%, it's going to be hard to reject. If I make it 0.1%, it's going to be really hard to reject. I'm probably never going to get it wrong on accident, but I'm also probably never going to get it right if there actually is a difference. If I make the significance level too small, I'm never going to find significant results. I'm going to make it too hard for me to cross that bar. If you make it too small, you might fail to reject the null hypothesis, even though the null is false. Right? If I pick a really small significance level, I might find only 200 spines on average. But my significance level was so small, that's still not enough to reject. But anybody can tell you if it used to be 250 and now it's 200, that's definitely changed. And we have a name for this type of error where you fail to reject the null hypothesis even though the null is false. This type of error is called, this type of error is called type 2 error, also known as a false negative. So reducing the chance of a type 1 error increases the chance of a type 2 error, and vice versa. We can reduce the chance of a type 2 error by making it really easy to reject the null hypothesis. But that makes it more likely we're going to falsely reject. We're going to have a type 1 error. It's a trade-off, right? It's a balancing. So the significance level, that's one reason why you just pick 5% every time, because otherwise you might be trying to get us to a specific result. Whereas if you say, I'm always going to pick 5%, then you've removed that variable and you're kind of removing the chance of bias. All right. The drawback with collecting more data, besides the logistical drawback, is we have to be out there for longer, is the following. If you collect a large enough sample size, you can always force a statistically significant result. Let's just go to an example. Suppose that I found an average of 249 spines. So my sample average was 249. Do you all think that's different from 250? No. And the standard deviation of the sample, still 18. Right? So some of them had like 280 spines, 290 even. Some of them had 220, 215, but on average, they were only one away from 250. But I collected 10,000 sea urchins. That means the standard deviation of my sample mean should be 18 divided by the square root of 10,000, which is, it turns out it works out to 0.18. And now I've built myself a normal curve. Sure, it's centered around 250, but 2 standard deviations only gets me down to 249.64. I've effectively hacked my data to create a statistically significant result that has 0 practical significance whatsoever. This practice is called p-hacking by some people. And so if you ever hear that term, basically it means I want a result, I'm going to collect data until I get the result I want, which is bad statistics. However, going from 32 to 60, that's probably good statistics. I had to go up to 10,000 in order to hack that data, right? So collecting more data is a good idea. You just don't want to do it in service for a specific agenda. That's the ethical statistics part. Okay. All right. Well, there is one other thing we could do that actually reduces. So collecting more data, a reasonable amount of more data, that reduces the chance of both type 1 and type 2. There's something else we could do that can reduce the chance of both type 1 and type 2. Does anybody have any ideas? Yes, that's exactly right. Have you read my notes or that was, no, great. That's good. Yeah, do it again. I mean, the gold standard for science is being able to replicate your results. So do the hypothesis test again with the same methodology or protocol. So we hop back in the bus, go back out to the tide pools, collect another 32 sea urchins, and maybe we do that 10 times. Each time we go out and we collect random sea urchins and we do a hypothesis test. And let's see, how about not just again once, but a reasonable number of times. And then we consider all the results holistically. So in our first one, we rejected. Suppose in our second one, we failed to reject. I'm going to do FTR. And then we failed to reject, and then we 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 failed to reject, and then we reject, and we reject. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we did it 10 times, and 6 out of the time, 10 times we rejected. 7 out of 10. And remember, it's not just a 50-50. We rejected 7 out of 10 times with a 5% significance level. That's pretty strong data. All right, we can consider that holistically to say these 3 were probably type 2 errors where I failed to reject, as opposed to these 7 were type 1 errors where I rejected and I shouldn't have. And you could even do a little binomial test if you wanted to, but we're not going to get to that level. It's just set out your methodology before you do it. What's the main drawback for this one? Yeah, it's costly, right? Doing it 10 times is much more costly than doing it once. So usually we don't do it a lot of times unless you're checking your work or you're still working on your methodology. We do it once and reject. There was only a 5% chance that we were wrong. That's good enough for publishing our research and exploring more and looking a little more deeply. But if you want to be sure, this is a good way to do it. The wrong way to do it is this. Suppose we do it once and we fail to reject. And so we do it again and we failed to reject, and we do it again and we failed to reject, and then we do it again and we reject and we republish that result. And this is super dishonest statistics, and it still happens. You can't just do your test until you get the result you want and only look at the result you want. If you're going to do it 4 times, you got to look at all 4 results. And this doesn't happen a lot. What happens more often is changing your methodology to get to the answer you want, or simply, that one didn't work. Let me study a different population. That one didn't work. Let me study a different population. That one didn't work. Let me study a different population. Oh, that one worked. This is the one I'm going to publish. All right, so we don't talk about the 3 populations that weren't different. We talk about the 1 population that was. So it's not as bad as like really lying about your data, but it's still specific. And it's hard because researchers get paid when they publish. And most people want to see interesting results. And I just told you that the null hypothesis is boring. So it's hard to publish the boring results, but it's still important. All right, anybody have questions about that? All right, we are going to talk about the ridiculous notation that statisticians came up for all of these things. I write and I say null hypothesis. The symbol is H with a little 0. It's pronounced H naught or H naught. Not as in 0, but I suppose it could be not as in not interesting. So you're often going to see something like H naught mu equals 250. This is the null hypothesis that the average number of spines is 250. And the alternative hypothesis is often written either as HA or H1. A for alternative, 1 because 1 is different from 0. And so you might see something like HA mu is less than 250. This is a 1-tailed hypothesis test. Or maybe I'm just saying HA. I didn't do research beforehand. I'm just curious. So I will just say mu is not equal to 250. This is a 2-tailed hypothesis test. The significance level, which is the probability cutoff, statisticians like the Greek letter alpha. So you're going to see alpha equals 0.05. That refers to a significance level of 5%. And we already talked about the p-value, the probability of observing data more extreme than what I have. Assuming the null hypothesis is true. So I'm going to write assuming null is true. All right. In a world where things are boring, what's the probability of observing extreme data? That's called the p-value. So you might see something like the p-value is less than alpha, so reject H naught. That's terrible statistics because that's not communicating anything to anybody who didn't actually do the statistics. The p-value is less than alpha, so reject H naught. What I'm really saying is the probability of seeing only 238 or fewer spines is so small that I conclude the number of spines has decreased over time from its original of 250. And that's a sentence that is still a little clunky, but at least it's understandable to, say, a marine biologist who's not a statistician. And I think that's it for the symbols that I have to worry about. Yeah. Okay. You are fully equipped to finish lab 3. Remember that when you're writing the report for lab 3, your goal is to translate your statistical analysis into definitely not this sort of thing here, right? Maybe something more like, we can conclude that the average number of spines has decreased since the previous research was published, right? Based on the low probability of what we observed or something like that. But you're communicating your statistical analysis to a non-statistician who's well-versed in the science of your subject, but doesn't spend their time reading statistics manuals. Okay, thank you.